Hello everyone, this is the Team Atlas Engineering Project 2 Bridge Design by Ben Taylor. The task that we are trying to achieve is to design a bridge that meets or exceeds all the stated goals and requirement, construct the bridge using the specified materials of balsa wood and glue, and test the bridge to find its maximum load capacity before structural failure. The objectives are to use balsa wood and glue, construct the bridge for under $4 million, make it weigh less than 20 grams, and it also needs to span a 10-inch, it also needs to be at least 10 inches long and 2 inches wide, and the ability to pass an eye hook through the center. It also can't have any structures below it that are supporting it. So the design that I chose for this was the Pratt truss. The reason why I chose a Pratt truss is because it is used all the time in civil engineering when you want a structure that is both simple and yet strong. And being simple and strong means that you can maximize the load capacity while minimizing the cost. It also keeps it simple to make physically. So the first thing that I did is that I used a modeling software that I'm very familiar with. I used Blender, which is the 3D modeling software. I then made all of the sticks, which are 3.45 millimeters square by 2 feet long, and then I constructed the bridge. Constructed what I thought would be a good Pratt truss. Now, one key feature of this design that I chose is I wanted to use the minimum number of different cuts. So as you can see here, there are only 7 different lengths. There's 31 centimeters long, 21, 16, 13, 9.7, 9.2, and 8.5 centimeters. Now, by doing this, I don't have to cut a million different pieces. I can cut like 2 31 centimeters, or 4 31 centimeters, just a fixed amount of each one, and I can do it beforehand. And it saves me time not having to cut a million different size pieces. This is really good for ease of construction and is a good habit going forward with other engineering projects, is to minimize complexity of construction. Now, the estimated costs. By using this software, I can figure out exactly how much it's going to cost because I know exactly how many pieces there are and I can count it. And with this bridge design that I decided to make, there are 55 individual pieces cut from these sticks. Cut out, there are 55 pieces, and they are joined at 168 spots. And like I said, using the software made this much easier. Now, for this design, 11 sticks were used, and there are 28 side joints and 8 corner joints. And you can see the total cost is $500,000, $538,200. So well below the $4 million goal. Construction. Like I said, the construction was made simpler by using the minimum number of different size pieces. So it used a lot of 9.2 centimeter pieces and 8.5 centimeter pieces. So I could just make a ton of those without making a bunch of custom sizes. And the way that I physically made it was by using the tools that I have personally. So I laid down a steel plate to be a nice flat bed to affix everything to. Then I put wax paper so that glue would not stick to it, because glue does not readily stick to wax paper. Then I held everything down using magnets, because I have numerous magnets, and I was able to cut the pieces and place them where they need to be, glue them, and then hold them together with magnets. And this also worked well for when I turned the 2D sides 3-dimensional and just held them up with magnets. And I was able to keep everything square and very nice. And most of my cuts were measured using a set of digital calipers, which are much more accurate than a ruler. They're good to about 1/1000th of an inch. So very accurate measurements could be made. And this you will see in the next slides. And you can see a list of the tools that I used below. Now, my final bridge versus my 3D bridge, you can see they are extremely similar. It's a dead ringer. They look almost identical. So I am very happy with the way that my real world bridge matched my 3D bridge in the software. Key design features. Now, some of the key design features are very important here. Notice at the bottom there, I decided to put members on top of other members so that they're pushing on top of each other. So the top one pushes on the bottom one. This is dramatically stronger than if you fixed it on the bottom, because it has the possibility of the wood delaminating. So instead of it supporting the full weight of it and then it's snapping, instead it's just going to rip off the top layer, and both of them are fully intact, but it just rips off the top skin, in other words, of the wood. So by putting them on top of each other versus bottom to bottom, it makes it dramatically stronger. This is an important key feature of the bridge design. And same goes for the top. I put crossing members so that if there was any sort of twisting moment in the bridge, it wouldn't twist and then leave both sides perfectly intact. I was afraid that the sides would be fully intact and then they would just twist out from each other. So those those diagonal top members helped prevent that. Now, testing and load capacity. This first design, it weighed 17.2 grams, so it was below the 20-gram threshold, and it held 9.08 kilograms. Unfortunately, I don't have a video to go along with this, so you're going to have to take my word for it, but I do have video to show. So this bridge that I put forward already succeeded, but you'll notice it was not a uniform failure. It held 9.05 kilograms, but it blew out the bottom. And as you can see in this photo, it demonstrates very well that all of the stress was focused on a single member. All of that load of the 9.5 kilograms was put on a single piece. So of course it failed. So the top and the sides were completely intact. However, the bottom blew out because it was not utilizing the full strength of the top and the sides. So this made me want to move forward with a design revision, even though I successfully completed what the project was requiring. So my new bridge design. You'll notice with this bridge design, instead of it being supported by that single bottom member, it's supported on the top, and it has 3 members on top of each other. Now, this is much stronger than if they were side by side. If you had many side by side, like 2 side by side, it would be twice as strong. By putting them vertically, one over the other, it is dramatically stronger. The more that you can increase the height here, the stronger it becomes. So you want it to have more vertical height there. So that's what I did. I stacked 3 members on top of each other, and then I also put crossing members so that they didn't just buckle out from underneath the sides, so that they could actually use the strength of it. You'll also notice that here is the bridge as it was after it's been destroyed. You'll notice that I put many more members through here to fully utilize the strength of the sides. In the first example, there were only 4 pieces, 4 of these balsa wood sticks holding onto that single side piece. So of course those 4 broke, and then the single piece underneath broke. By having a ton of members here, it can fully utilize that side strength, and then by having 3 stacked on top of each other, that's where the majority of your strength comes from. Now, this bridge costed about $200,000 more, the total cost including labor being $763,000. But you'll notice that the maximum load capacity went way up. It's a marginal increase in cost, but a dramatic increase in load capacity. It's more than 3 times the load capacity, with only 20-30% more increase in cost. So that is a major improvement in the design. You'll also notice that the failure was completely uniform. As you can see here, it was not a single member that broke out or just 4 pieces that broke out. The whole entire bridge destroyed itself. And that's the kind of failure that you want, because if it fails at a single small piece, then your bridge wasn't properly used. It just failed at its weakest point. But here, there was not a single weakest point. It was very uniformly destroyed, and that is what I wanted. And the professor will show you that video that is linked in a different YouTube video. So, things that I've learned from this. Do not assume that the load will be applied evenly. In the first bridge design, it failed at its weakest points, which were just 4 cross members as well as 1 single side member. I didn't realize that I wasn't actually using the sides of the bridge in that example. That was just 4 members and then a single long piece. So with this example, I learned, look at where the load is actually being applied and make sure that the bridge is being used in its strongest way. Make sure that the wood that you're putting underneath it is actually supporting it and not just there for decoration. So kind of think critically about where the load is applied and make sure that it's being supported properly. Now, if you have any questions about my bridge designs or any of the thinking that went behind it, please send me an email at btaylor369@ivtech.edu. Please let me know if you have any questions about this. Thank you.